So after the introduction of binomial distribution and Poisson distribution, now we are ready to study the first model for random graphs, which is called Erdős-Rényi model, and it was given by two famous mathematicians, Hungarian mathematicians actually, Erdős and Rényi. And in this model we consider the version in which what we have to give are two parameters for our graph, and the two parameters are the n, which is the number of nodes, and p, which is a probability, so it needs to be between 0 and 1, and this probability describes like what is the probability of an edge appearing between pairs of nodes. And you can see here that basically if you fix the probability of the edges between vertices, then the probability that a particular graph exists is given by this formula here, which we can interpret in such a way that we have m edges, and in that case each of the edges, they have probability p to appear, and so this is going to be p to the power of m. And the second part of the formula describes the case when we have no edges between pairs of nodes. So that's 1 minus p, of course, that we don't have an edge. That's the probability. And this one here up here is the in the exponent is n choose 2, which is actually the number of node pairs we can have in the graph. So please look it up in combinatorics, this notation. So we have a number of pairs we can form between, so how many pairs of nodes we can form, and we have to subtract m, because we know that we have m, the number of edges is equal to m in this case. Now, of course, we cannot calculate this one because we don't know the value of m here, because it's not given by the model. So at this point, this is only a theoretical model. And having said this, it's also easy to see that we don't have the number of edges fixed here. We just give the number of nodes and the probability that an edge appears between a pair of nodes. So we can have the case when we obtain an edgeless or edge. So basically an empty graph, but empty in such a way that it doesn't have any edge. So it can also happen by chance, and it can also happen that we have a full graph. I mean, I'm talking about the cases when p is not equal to 0 or 1. But of course, with very low probability, we can get one. Now, what we can calculate with the previous formula is the expected number of edges in our model network, and for that one, I need to mention here, so I need to tell you. I wanted to select that part, but it's impossible in this case now. Okay, so I wanted to talk about this ensemble expression here. So this is coming from physics, I guess. Physicists like to use this expression, and so the exact definition is not that important. What may be important is to imagine it as a huge set of all the possible graphs which we can obtain by this Erdős-Rényi model once n and p are given, and the probability that a certain graph with m edges is getting realized, it can be expressed by this formula here. And you can see that from the previous slide we have this part of the formula. So let's just get back to it. Okay, so you can see that that this is the probability of a certain graph, and now this one is multiplied by this factor here, which is n choose 2. So that is the number of different pairs we can get, and once we get that number, then that number choose m expresses that how many different cases we have for so how many different cases we have that we have m edges between these pairs. And what is really important here is that this formula altogether is actually the formula for the binomial distribution, which we discussed at the beginning of this today's lecture. I just did not mention there that the distribution function there has this kind of formula there. Okay, so it's very important to see that binomial distribution and the Erdős-Rényi graph model, they are basically the same thing. Now, after this, you might remember our notation for moments, and you also might remember that the first moment, which is denoted by this angle bracket, is nothing else but the sum of all the possible cases. So m goes from 1 to infinity. And what we need to put here into the sum is m times the probability of what we just discussed here. Okay, so m times the probability of m, and you can well, do the calculations if you want. Well, first of all, I mentioned here infinity instead. What we can see here is definitely a finite number. Of course, we can go up to infinity, but I mean, above this number, this particular number, the probability is 0. So that doesn't matter in the sum. So you can do the math, and then it turns out that this formula, if we multiply it by m, and then we do the summation, then this is what we are getting. So the mean value for m, so the number of edges in an average graph, it has this value. So continuing the discussion, so I'm just repeating here the formula which we obtained, but we can also, so okay, so this means that we can we don't know like what is the exact number of edges in our model for a graph once we have n and p, but we definitely can get the average value or the mean value of it or the expected value of it. And we can do also the same calculation in a different way. And okay, so that was the mean value for the number of edges. Now we can also do the same calculation for the degree. Okay, so that of course relates to the number of edges, and we are actually going to use it. But this is for the degree, so you might remember that it was denoted by k. And now we substitute k with 2m divided by n. You can get back to, I mean, you can look it up back in the previous lectures that we, I think, derived this fact that the average degree in a graph with exactly m edges has this kind of formula, so 2m divided by n, where m is the number of edges and n is the number of nodes. So this is the multiplication factor which we need to multiply pm, so the probability of m. And again, if we do the math, then we get this formula here, and this turns out to be n minus 1 times p. And well, we are just using the fact that n is a constant here. So the average degree, once we have n and p given, then we can get it as a closed formula. So again, that's not describing the degree sequence or anything about the degree apart from the average degree for the entire graph. Now we can say, or we can also see that if we have a particular node, a particular vertex in the graph, then it's connected to n minus 1 other vertices with probability p, independently from each other. Now the probability of that node connected to k particular other vertices and not to any other vertices is it can be expressed by this formula. Why? Because p to the power of k, so k times so basically p times p times p times p up to k times this multiplication, so that expresses how many times it's connected to those particular nodes, and this is the leftover part. Okay, so 1 minus p is the probability that it's not connected to those k nodes, and I mean to the other nodes apart from those k, and how many of them we have, n minus 1 minus k. Moreover, we have n minus 1 choose k ways to choose those k other vertices. So the degree distribution is going to be having this formula here for the Erdős-Rényi graph. And again, this is nothing else but the binomial distribution. So to the board is written here, so if this lecture was happening in a classroom, then I like to write this formula down to the whiteboard for later reference. So with the degree distribution, of course, we can do interesting analysis, especially the case when we have n, so the number of nodes make, I mean, in a very as a very large number. So if you want, we can also make it up to infinite, but practically it's not that important or not that interesting. But let's say that n is, so the number of nodes is a huge number, and so we can see that if we have a large network, a very large network, so n is really large, then the mean degree is actually becomes also a constant, more or less, because adding for more and more nodes, we don't really change the average degree in the graph too much. So, for example, a typical number of friends a person has does not depend strongly on the total number of people in the world. So usually a person has 100 friends, let's say, or 50, or maybe even more. But the fact that that we have 7 billion people on the world, or maybe next year, or in two years or 10 years we will have 10 billion, it doesn't really change how many friends we have, right? So that's the motivation. And well, we have this formula P is equal to C over n minus 1, where C is the number of I mean the average mean, or sorry, the average degree, so the mean degree. Okay, and how did we get this one? Okay, so let's see what we have here. Okay, so you can see we got that formula from here. Okay, so the average degree of a graph, it can be denoted by this one, but according to the previous lectures and also in the notation in the book of Newman, the average degree is denoted by C. Okay, sorry not mentioning it here. So what we have is C equal to n minus 1 times P. And of course we can rearrange it, which doesn't make too much sense, but for the analysis we can do so. So by that one, what we get is P is equal to C over n minus 1, of course. Okay, so let's see what we can get with that. So definitely if n approaches infinity, or n becomes really large, then C over n minus 1 is going to be very small number. So what we need to what I'm trying to get here is that that the part of the formula, so this part of our degree distribution, we would like to simplify it. Okay, so let's take the logarithm of it, which is interesting for the particular reason that by that one we can basically so to say get rid of the exponent. In fact, we are not getting rid of it, instead we are moving it from the exponent as a multiplication factor. Okay, so this is according to the properties of the logarithm function. So we are moving the exponent here as a multiplication factor, and what we have remaining is 1 minus C over n minus 1, where we substituted P with C over n minus 1. Okay, and it's approximately equal to this expression here. Okay, now let's see what's going on here. So first of all, the multiplication factor remained, and what seems to be the case that we got rid of logarithm and 1 minus this part, which, so the C over n minus 1 is still here. So what we got rid of is the logarithm 1 minus this thing. And you can also notice the minus sign here. So what is the case here is that in fact that the logarithm function, if we take it as 1 minus x, then basically I think the slide is wrong, so this should be equal to minus x, by the way. So if x is a really tiny number, then this function here is actually behaving similarly to the minus x function. So it's approximately the same thing. And this is why we can get rid of the logarithm and the 1 minus part, but we need to have the minus 1 multiplier here. And yeah, sorry. The thing is that by simplification we can get minus C only as approximation. Okay. So that's the substitution, and hence we obtain the simplification for this part of the probability distribution as exponent of minus C. And why? Because here we took the logarithm, and then we ended up having minus C, like approximately equal. Okay, so that's going to be the simplification. The other simplification was the multiplication factor at the beginning, which we can also substitute with this formula here. Okay, this is just mathematics, some magic. Okay, and after this we can substitute pk, or well, replace the formulas in pk the first part with this factor, the second part remains to be p to the power of k, so we don't change that one, and the third part is e to the, so exponent of minus c. And after some replacement, so p is replaced by c over n minus 1, then doing some simplification, what we get is this formula. And you can get back to the previous whatever slide where we discussed the Poisson distribution, and you can see that for the Poisson distribution we had exactly this formula as a distribution function. So it's not surprising that for small networks, so the conclusion of this one is that for small networks the Erdősényi graphs, the degree distribution follows binomial distribution, and for really large Erdősényi graphs or infinite graphs of Erdősényi type, they follow Poisson distribution as degree distribution.